Alright guys, so today I'm going to show you another situation. We're going to be working with my friend Chewbacca here, or Potato Bacca, and we're going to be working to look at some of the things that we've already done, talk about some of those principles, see how they apply, and then we're going to add in a new idea, which is called conservation of energy. Alright, so we're going to go ahead and start with some things that we've already done. Alright, so let's first look at Chewbacca. So when Chewbacca is right here, okay, let's say that he's about 1.5 meters off the ground. He's just sitting there in my hand. So first, I'd like for us to draw a free body diagram of what's happening to Chewbacca right now. Okay, so as he's sitting there, you've got what are the forces acting on him. All right, so at first, when he's in my hand, here's Chewbacca. What are the forces acting on him right now? Well, hopefully you recognize that gravity's pulling down on him, right? The force of gravity is always there as long as you're somewhere where there's another object that could exert that gravity on you. So force of gravity is pulling down, all right? What else? There's got to be something else, right? Otherwise he would be falling down. Well, hopefully you're recognizing that my hand is pushing up. There's the normal force of my hand, which is pushing up. And that's it. There's nothing else touching him, and there's no other contact forces that we're worrying. He's not magnetic, he's not electric, he doesn't have an electric charge. So none of those other forces are going to come into play here. All right? Now, the second thing I want you to do is when I hold him and I drop him, as soon as I let go, we want another free body diagram. All right? So here we go. 3, 2, 1. Goodbye, Chewbacca. There you go. So what were the forces acting on him when I released him and he started falling? Hopefully you recognize the force of gravity, which should be the same as it was right there. So I'm going to try to do it about the same length there. And that's it, right? Because like I told you at the beginning of this, kind of this part of this unit, we're not going to consider air friction, air resistance. So that's it. You've got force of gravity down. That's why he falls, because there's a force pulling him down and nothing else balancing him to hold him up. Now, with this, we could actually figure out the speed at which he hits the ground, right? We know how to do that. We've done some kinematics. So let's do that. Let's talk about what speed will he be going when he hits the ground. So I said at the beginning that he was about 1.5 meters above the ground. So we're going to start at 1.5 meters because he was up here. I'm going to call the ground 0. You could make this 0, and that would be negative 1.5 if you wanted, but I'm going to go ahead and go 1.5. The ground will be 0. The initial velocity, when I'm holding them, right as I release, his initial velocity is still going to be 0. So 0 meters per second. I don't know the final speed. I do know his acceleration because the only force is the force of gravity. So therefore, his acceleration here on the surface of Earth will be negative 9.8 meters per second squared, and I don't know the time. All right, but what I would like for us to do is calculate how fast he'll be going when he hits the ground. We could calculate the time as well, but what I want us to do right now is to calculate the speed at which he'll be going. So you look at your equations, you think about them, you say, okay, which equation is going to be best, and you hopefully will choose this one, the one that does not have t in it. So v squared equals v naught squared plus 2ax minus x naught. So the v squared, that's what I'm looking for. The v naught is 0, 2 times negative 9.8 times the x, which was 0 minus 1.5. And then I should just be able to go ahead and put all those numbers into my calculator. 2 times negative 9.8 times 1.5, negative 1.5, because 0 minus 1.5 would be negative. I should end up getting v squared equals 29.4. I am going to need to take the square root of that, and when I take the square root, I end up getting 5.4 meters per second. Now it is a velocity. Because I took a square root, it should be plus or minus. Anytime you take that square root, the answer should be plus or minus. Your calculator won't tell you that, but you know that anytime you choose the square root, it's plus or minus. We do know that by the time he gets down to the ground, he's traveling downward, and so my velocity here should be negative 5.4 meters per second. The speed would just be 5.4, right? But for velocity, we need a direction on there as well. So there we go. We've got velocity is negative 5.4 meters per second. Now, with that, what I want to do is now introduce you to another idea. I'm going to show you some other physics, some other things that we know about the situation that will help us to answer this question in a slightly different way. All right? So, again, let me present you with Chewbacca. Okay, so Chewbacca right here. We're going to talk about energy now. Now, there's a couple of things. I'm not going to talk about everything possible about energy, but we're going to get introduced to it. So the two types of energy we're going to look at here at the beginning are types of energy called kinetic energy and gravitational potential energy, right? Now, kinetic energy is the energy of motion, and the energy of motion, we can calculate it by using 1/2 mv squared. Some of you may know that already, but if not, here we go. Just like that. Now, what that is it's 1/2 times the mass times, now they do use a v here, but it's not velocity, it's speed, okay? Because it doesn't matter which direction you're going to end up getting speed, okay? It's going to be squared, so it really doesn't matter. So this is always going to be speed. Now this is going to be nice in some ways. You'll remember with kinematics, we could only deal with straight lines, up and down, side to side. Energy is going to allow us to work with some other directions, and we'll be able to deal with curves, and so it'll be nice. It'll open up some more doors for us. Yeah, we love kinematics. Kinematics works really nicely. You're probably getting a little bit comfortable with it now, but energy is going to be helpful in some other places. Okay? Now, the other type of energy is gravitational potential energy. And your gravitational potential energy is mgh. Now, sometimes you'll see this written slightly different. Sometimes what you'll see is the change in the gravitational potential energy is equal to mg delta h, because the mass isn't changing, g, gravitational acceleration, is not changing, possibly the height is the thing that's changing. Height, now this is h for height, but it's also sometimes just the distance between your 0 and wherever you are. We'll look at that in just a minute. All right, so these are the two types of energy. I want to go through this example with Chewbacca and see if we can understand what those are doing. I'm actually going to go through and show you two different ways in which we can interpret this situation. All right, so one thing about gravitational potential energy is that gravitational potential energy is always an energy between two objects. It's always part of a group, a system. All right, now that's important because an object by itself does not have gravitational potential energy. This object right here, Chewbacca, he does not have gravitational potential energy. Now, when we talk about him and the Earth together, they have potential energy because of the way that they interact with each other. Let me show you. So, we started with Chewbacca up here 1.5 meters off the ground. What type of energy does he have right now? Well, when he's at rest, he doesn't have any kinetic energy. And because we're just talking about him, he doesn't have any potential energy either. Now, when I release him, there is an outside force. Because I'm just talking about him, there is the outside force of gravity which is pulling down on him. Now, that force can do something that we call work. Work is a change in energy. All right? Now, we can often calculate this by multiplying the force being exerted times the distance that the object is traveling. All right? Now, this is going to get us into a little bit of trouble because we don't know how to calculate force yet. Well, no problem. The force of gravity is really, really simple. In order to calculate the force of gravity, now we've been talking about the acceleration of gravity up to this point. In order to calculate the force of gravity, all you have to do is multiply the object's mass times the acceleration of gravity. And if you multiply those two, then you know exactly what force. Remember last time in class, we talked about that all things accelerate at the same rate, but an object that's more massive, more larger, will have a larger force pulling on it. Well, this is how you do that. You make sure that your mass gets multiplied by g. The bigger your mass is, the bigger the force is. But the acceleration is still the same. Acceleration is still the same. So what I'd like for us to do is look at the situation of Chewbacca and see if we can use the information that we have. One of the neat things is that energy is conserved. As long as there are no external forces, as long as there's no outside forces, energy will always be conserved. All right, what that means is that the energy in the beginning needs to equal the energy at the end. Now, if there are outside forces, then we need to add that on at the end to either add on the energy or take away the energy. All right, so here, let me show you. Let me show you. So again, when we had Chewbacca right here, we stated that he had no kinetic energy and no potential energy because we just are talking about Chewbacca, not the Chewbacca Earth system, just Chewbacca. So right now, no kinetic, no gravitational potential. So initial, he's got 0 kinetic and 0 gravitational. Now, that initial energy should be equal to the final energy. Okay? So, when I take him and I drop him, there is an outside force acting on it, right? By the time he gets down to the bottom, he should have some kinetic energy. So in the end, he's going to have kinetic. Before we said that the kinetic was 0 and the gravitational potential was 0. But now, right before he reaches the ground, he's got some kinetic energy. The kinetic energy is that energy of motion. He's got some speed right before he hits the ground, so he should have that. All right? Now, there was an outside force. Gravity was pulling down on him, right? Gravity was exerting a force down on him. Therefore, gravity is going to do work. Gravity is going to cause him to gain energy. He still has no potential energy because we're not looking at the Chewbacca Earth system. So 0 potential, but we are going to include the work being done. Now, gravity does this work, force times distance. Now, that work being done is being added to what he had in the beginning. So he started with this. He adds the energy that gravity is giving him, and it should end up resulting with this. So we go right here, we're going to put the work, and we're going to add in whatever work was done. Now, we can put this all into an equation, okay? We can go 0 plus 0, which is 0, plus the work, and work is force times distance, so that force is the force of gravity, and that should be equal to the kinetic energy plus 0, and kinetic energy is 1/2 mv squared, just like that. All right? Now, with that, we can calculate the force of gravity. The force of gravity was mg. I need to know the mass of Chewbacca. So Chewbacca's mass is about 500 grams. So I'm going to put in the mass times g, which is 9.8, times d. D is the distance over which that force was exerted, which we said was 1.5 meters. Now that should be equal to 1/2 times his mass, which again is 0.5, times his final velocity squared. Now what you can notice, I hope, is that we can calculate his final speed once again, but this time using energy. All right, so we can do 0.5 times 9.8 times 1.5, so 0.5 times 9.8 times 1.5, and then we're going to divide by the 0.5 and by the 1/2. So I take these, multiply them, divide by the 1/2, divide by the 0.5, and I end up getting 29.4. I'm getting a weird sense of deja vu here, and when I square root that, hopefully I get the same thing that I got last time, which is 5.4. How about them apples? Eh? 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 Same thing, right? So we were able to use that idea of gravity adding energy in to Chewbacca in order to get the same speed that we got using kinematics. All right, now this is a new idea, so it's a little bit weird, a little bit more challenging perhaps, but it gives us the same thing. And in some situations, we will only be able to use this one. Now, I do want to share with you this. Okay, so in the beginning, we said that Chewbacca had zero energy, right? He had zero kinetic energy and zero gravitational potential energy. And then we said that as he falls, gravity was doing work. So as time progressed, so this is our energy table right here. Initially he had zero energy, but as he fell, gravity was giving him energy. So then he had a little bit of kinetic energy, right? He started speeding up. And then he had a little bit more kinetic energy, right? As gravity continues to pull down, he gets more kinetic energy, and so gravity doing work is actually adding blocks into our stack until we get to the point where he has a certain amount of kinetic energy, which is right before he hits the ground, which corresponds to his speed. And so gravity, as work, was adding blocks into our stack there. All right? Now, that having been done, I want to show you a slightly different way of looking at this situation. So let me erase what I have over here. Remember, we had the same speed. All right. All right. There is one more way to look at this situation. We've looked at it through kinematics. We've looked at it through just looking at Chewbacca and the work being done by gravity. So we've looked at it that way. Our last way is we're going to look at the Chewbacca Earth system. Okay? Now what that means is that gravity is now inside of our system. So when we say system, we just mean that group. Now that means that gravity is now inside our system because we're looking at Chewbacca and the Earth together. So gravity is now an internal force. It's inside of our group. Now what that means is that gravity won't be doing work this time, right? Before we said that gravity was an outside force, so therefore it was pulling down on Chewbacca doing work. This time, gravity is going to be an inside force, an internal force, all right? So what's going to happen this time? Well, this time we've got Chewbacca here, but because we're talking about the interaction between Chewbacca and the Earth, and they are a group, this time Chewbacca has what we call gravitational potential energy. Now, gravitational potential energy is the energy because of his height, because of his distance from the surface. Now, we can make our initial position, we can make our zero position wherever we want. I'm going to make zero the floor, but you can, again, very similar to what we did with kinematics, you can make your zero wherever you want, but I'm going to make zero the floor, all right? So this time, he's going to have a certain amount of gravitational potential energy because of the place that he is relative to the Earth. All right, so if we look at our blocks, this time it's not empty. This time he's going to start with a whole bunch of gravitational potential energy. So if we look at our initial and final, remember we looked at kinetic energy first. Does he have any kinetic energy when I'm holding in my hand? No. So no kinetic. But because of his height and because we're looking at the whole system, he now has gravitational potential energy. Okay? Then, in the end, right before he hits the ground, he's going to be all the way down at the ground. He's going to have some kinetic energy now. But because gravitational potential energy depends on the height, right? This is what we said at first. mgh, and because right at the ground his height is going to be 0, then he will not have any gravitational potential energy. Now, last time we added in work because we were just looking at Chewbacca and gravity was therefore an outside force. But remember, gravity is the only force acting on him as he falls, so there are no outside forces this time. Gravity is inside of our group, inside of our system. And so this time, we don't need to add on any work. The amount of work being added on is 0. Now, what happens as Chewbacca falls? As Chewbacca falls, this time, as his height goes down, as this number goes down, it's going to cause this number to decrease. But that energy is not disappearing. That energy is turning into kinetic energy, right? So as he falls, gravitational potential energy decreases, but kinetic energy increases. So as he falls right here, he's got a certain amount of gravitational potential, and he falls a little bit, and he's moving a little faster now. Some of that energy is kinetic. He falls a little bit further. He's going a little faster now, so now he has a little bit more kinetic energy. He falls a little bit further, and so that continues to move over. The gravitational potential energy continues to turn into kinetic energy until right before he hits the ground, and all of that energy does not fall over, but it is all in the kinetic energy pile there. And so this time, rather than work adding energy in, we just have a transfer of energy from one type to another. There's no outside forces, so we don't need to add in any new blocks. We just keep the blocks that we have. All right? So let's see if we can do the math with this one. So you'll notice that we have 0, 0, and gravitational potential energy, which is mgh. So our mgh, and then in the end, we're going to have 1/2 mv squared. Now, if it's helpful, you can put a little 0 here to remind you that this is initial, though I did put it under my initial label. And over here, you can put a little f for the velocity final, because that is going to be our final speed there. All right, now we can put this in. We said his mass was about 500 grams, so 0.5 kilograms, times gravity, which is 9.8. And some of you may be asking, but isn't g negative 9.8, Mr. Bywater? No, g is 9.8. When we look at kinematics, we're using it as an acceleration, which is a vector. So we have to put the negative because it's down. In this situation, energy is not a vector, so we don't need the positive and negative there. All right, so 9.8 times the height, I'm going to say my initial height is 1.5, and this should then be equal to 1/2 times his mass times the final speed. And so then we go ahead and calculate. We'll go 0.5 times 9.8. Man, I get this feeling of deja vu all over again. Whew, this is weird. So multiply, divide by the 1/2, divide by the 0.5. Man, I feel like I've said that before. All right, and I got 29.4 equals v squared. I feel like I've seen that number before, y'all. Square root both sides, and we should get beep, 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 beep. Again, 5.4 meters per second is our final speed there. So what I want you to see is just that we have different ways in physics of dealing with the same situation. We've got our kinematics, which allowed us to look at the dropping. We looked at it from the perspective just of Chewbacca, where gravity was an outside force doing work. And then we looked at it from the situation where we looked at Chewbacca and the Earth together, and therefore gravity was an inside internal force, which allowed us to have this gravitational potential energy. In the end, this is what I want you to remember. You need to know that the initial kinetic energy plus the initial gravitational energy plus the amount of work coming in should equal the final kinetic energy plus the final gravitational potential energy. And yes, you do need the G there because we're going to add in one other type of potential energy by the end of the year. All right? So this is what we were doing, right? Initial kinetic, initial gravitational, and the work coming in. That was equal to the final kinetic and the final gravitational. Same thing here. Initial kinetic, initial gravitational potential, work being added in, final kinetic, and final gravitational potential energy. All right? I hope that was helpful. We will be working on that significantly in class next time, and hopefully you'll get a little bit more comfortable with this new idea of energy and conservation of energy. See you then.